We have all committed mistakes in our studies in mathematics. I'm not talking about mistakes caused by carelessness or lack of knowledge, or even foolish notation mistakes. Some mistakes are just well hidden and subtle. My goal in this video is to entertain you with a collection of incorrect conclusions or fallacies that help us better comprehend fundamental parts or concepts in mathematics. We should have a far greater understanding and respect for the subject matter as a result of these mistakes. Some of them can result in some extremely intriguing mathematical concepts. This video will be divided into 3 parts based on their complexity, and this video will be my entry for the Summer of Math Exposition number 2. As we begin our journey through the various mistakes that occur in mathematics, it is natural that our first stop should be in the field of arithmetic, because it is typically the first encounter that one has with mathematics. So, let's begin our journey. A recently reported building project illustrates a typical problem in working with percentages. Parking lot will be landscaped, which implies making each parking lot a little smaller. The length and the width of the spaces will be lowered by 4% and 5% respectively. As a result, it is calculated that the area of each space will be decreased by 20%. Right? No. This is a tremendous mistake. Consider the following, where A represents the current parking space's length and B indicates its width. To begin, we depict the area of an existing parking place, which is its length multiplied by the width. Then, the new parking space would be the original length subtracted by 4% of its original length, multiplied by the original width, subtracted by 5% of its original width. This will give us 96% of the original length, multiplied by 95% of its original width. If we go ahead and multiply them, we will get 114 over 125, multiplied by the original length and width. Then, as a final result, we would get 0.91 of the original area. This demonstrates that the error was rather significant, since the spaces were really decreased by around 9%, not 20%. Consider the following question. Jack Glover wants to make a 20% antifreeze solution by adding enough 50% antifreeze solution to 16 gallons of 5% antifreeze solution. How much of the 50% solution should he use? When you hear this question, you will immediately resort to a mathematical solution. However, when Elizabeth Berman Applebaum of Shawnee Mission spoke with a service station employee, he claimed to have solved this type of issue in mathematics classes, but no one does it on the job. They put the antifreeze in the car to see what temperature it protects against, then they add enough antifreeze to bring the temperature up to the appropriate level. This demonstrates that math is not always employed in what appears to be a math problem. The phrase "one learns from mistakes" is especially true when it comes to algebra. Naturally, one can make a mathematical mistake, casual omission, or even ignore some basic algebraic laws. A breach of these algebra principles will almost always result in ridiculous results. These mistakes, although frequently funny, may also be quite instructive. Let's start with an equation that contains ones that are being subtracted and added simultaneously. These numbers can be grouped into a series as follows, whereby this grouping, you will get zeros added which would at the end result with 0. These numbers can also be grouped as follows, whereby this grouping, 1 will be subtracted to a bunch of zeros, which will at the end result with 1. It would be reasonable to assume that 1 equals 0 based on these two outcomes for the value of s. The convergence of this series is to blame for this mistake. A totally convergent series is one that not only converges to a definite value at infinity, but also converges when all the plus signs are changed to minus signs. A conditionally convergent series, one that is not absolutely convergent, was demonstrated by the German mathematician Bernhard Riemann to be one in which the terms might be adjusted to equal virtually any integer. A coin is placed in a box by a magician. After half an hour, he takes the coin out of the box and replaces it with a second, third, and fourth coin. After a quarter hour, the magician removes one coin and replaces it with 3 fresh coins. After 1/8 hour, the magician removes another coin and replaces it with 3 new coins. He repeats this method for an hour. How many coins will be in the box at the end of the hour? Now, one might think of 2 solutions. The first one, which is that at each phase, 1 coin is withdrawn from the box and 3 new ones are inserted. This implies that 2 coins are added to the collection in a box at each stage. As a result, after n steps, the box will contain 2n plus 1 coins. The magician will have accomplished an endless number of steps in 1 hour using this approach. As a result, the box should contain an endless number of coins. And the second solution, which is what if we ask ourselves, what is the final coin in the box? Each coin placed in the box might be given a number. Assume that n is the value of one of the coins in the box. The coin will then be withdrawn from the box at the nth step of the operation. That would indicate that every coin placed in the box would be removed at some point. As a result, there will be no coins in the box at the end of the hour. This indicates that 0 equals to infinity. So where does the error lie? I'll leave that to you, but as a clue, consider the peculiarities of infinite series. Geometry is frequently referred to as a visual component of mathematics. We have a tendency to trust what we see. Geometric diagrams, however, continue to be useful in identifying geometric properties and planning to prove geometric connections. Geometric diagrams are quite important, yet they must be carefully reviewed. Humans are naturally drawn to paradoxes, optical illusions, and strange objects. The obsession in impossible geometric objects stems from the same source. They are defined by mathematicians as figures that cannot exist in a physical form in our 3-dimensional Euclidean space. These figures are nearly always clever optical illusions. The illusion is generally caused by these bodies' 2-dimensional perspective representation, which we mistakenly interpret as 3-dimensional. Here are some of these perplexing mathematical objects. Although such a thing may be represented in 2 dimensions, it's not mathematically viable for it to exist in the actual world. However, certain models of impossible things can be created using anamorphosis, which is a way that maintains the illusion when viewed from a very particular location. Because altering the viewpoint or rotating the item disrupts the illusion, many of these models rely on forced perspective or making elements of the model appear to be farther or closer than they are actually. An interactive impossible object is defined as an impossible item that may be observed from any angle without destroying the illusion. We begin by placing 2 coins that are touching on a table. One coin will remain fixed, while the other will spin around the first coin without slippage, until it reaches the starting point. That is, until the center of the revolving circle hits the starting point. Because the coins are congruent, the question is how many times the rolling coin has spun after traveling precisely once around the stationary coin. 1 time is the most common response to this question. However, this is an incorrect response. So what is the right response to this question? We will track the movement of the moving circle center at each of the stationary circle's quarter circles. This might be the location where the moving circle center travel along the dashed line circle. Because the point P is now at the top, we can see that the movable circle has rotated once. As a result, by the time the rolling coin returns to its initial location, it will have completed 2 revolutions. This is counterintuitive and hence unexpected, which usually results in an incorrect response to the original question. In addition, the path that point P takes is known as an epicycloid. Because the two circles in the question are the same size, this epicycloid with one cusp is known as cardioid. A team is made up of 3 players. These 3 players are blindfolded and stand in a circle formation. They will be given a hat to wear while blindfolded. Using a fair coin, the game coordinator places a gray or white hat on each of the participants as follows. If the coin lands on heads, the player is given a gray hat. If the coin reveals tails, the player is given a white hat. When the blindfolds are removed, each player is able to view the hats of the other players, but not his own. A player can either try to predict the color of his own hat or declare "I pass." If at least one player correctly guesses the color of his own hat and no player wrongly guesses the color of his hat, the team wins. Otherwise, the team will be defeated. The players are unable to communicate with one another. Nonetheless, they can agree on a common plan to win the game. Which of the following tactics would increase the odds of the team winning? Solution 1. The team must have at least one right guess in order to win. The more answers they receive, the more likely they are to win. As a result, the plan will be for all 3 contestants to predict. Solution 2. To avoid losing, no player can choose another false color. The more comments one receives, the more likely it is that someone would predict the incorrect color hat on his head. If no one speaks, there will be no accurate guess. As a result, the best approach would be for only one player to predict the color of his own hat. Solution 3. 1, 2, or 3 players can estimate the color of their own hat. The more individuals that guess, the better the possibilities of winning with right responses. Nevertheless, the likelihood of someone replying incorrectly also grows. When fewer people react with guesses, the chances of a false guess decreases, while the probability of a true guess decreases. The optimum solution is somewhere in the center. The best technique is for precisely 2 individuals to guess. These 3 strategies gave 3 distinct results. Which one is the right answer? Consider the following 3 players, each with their own set of options. A, B, and C will represent 3 players. There are 8 options to consider. Solution 1. Assume that both players A and B picked a white hat, whereas player C guessed a gray hat. In that instance, choice 4 would be the only viable alternative. As a result, using this technique, the probability of winning is 12.5%. Solution 2. This time, we'll assume that player B correctly predicted that he was wearing a gray hat, and that players A and C did not answer. In other words, they just passed. The team will have won cases 3, 5, 7, and 8, but will have lost all of the others. As a result, the likelihood that the team would have won employing this method is 50%. Solution 3. Now we'll assume that player B guesses he had a white hat, and that player C guessed he had a gray hat, and that player A that just passed. Option 4 and 6 would have been won by the team in this situation. In this case, the likelihood of the team winning is 25%. Each player's choice of hat color is an individual event. Solution 1 has the lowest likelihood of winning, whereas Solution 2 has the highest possibility of winning. It is therefore desirable to assume that Solution 2 is the best option. There are, however, better options accessible. Consider the 4th strategy that the squad can employ to win. Players A and B see the color of player C's hat immediately after removing their blindfolds. If the hat on player C is white, then player A would immediately pass, or he would wait until after B passed. Player B does the exact opposite. They can notify player C about the color of his hat in this manner. As a result, player C will be able to correctly identify the color of the hat on his head. The likelihood of winning the game is 100% in this case, indicating that this is the optimal winning strategy. We are once again tempted into embracing a reasonable sounding method until we opened ourselves up to a more logical action. I hope you liked this journey through a variety of mathematical mistakes. Some mistakes were quite amusing, while others inspired famous mathematicians to work even harder toward profound results. Still, others allowed you to appreciate the power and beauty of mathematics, while also recognizing how the structure was sometimes based on premises or approaches that led from mistakes to unexpected successes.